All right, so now we're going to get to our second problem, which is a Frisbee problem. So we're going to make a Frisbee launcher. So it's going to basically launch basically a Frisbee. Actually, we can see a little schematic here. We're going to launch a Frisbee in this direction, and it is going to have basically 0.5 meter diameter. It has a mass of this. We want a linear acceleration of this, an angular acceleration of this, and we need to solve for F1 and F2 to meet the criteria. Ignore friction between the Frisbee and launching pads. The IG is this for a thin disc through the axis perpendicular to the face of the Frisbee. And let's get at it. So we're going to idealize our system first. So this is F1, this is F2. So again, we're ignoring friction. We have our coordinate system. That's step 2. Step 3 is going to be our basically free body diagram, which is effectively this right here. So we're shooting that Frisbee through. There's going to be some force here, some force here. We are actually told, actually, what is our force? We're solving for force 1 and force 2. Exactly. We're given the IG there. We're given the mass. We're given that the diameter is 0.5. So this is our free body diagram. We're going to ignore, basically, so we're moving. There's going to be some acceleration in this direction. So for our kinetic body diagram, we are going to have, this is going to be our G, we're going to have some mass acceleration in the Y direction. And there's also going to be some, basically, angular IG alpha right here. So our body's going to be spinning as well. And you can kind of see our spinning direction here. So this is our kinetic body diagram. So now we need to write out our equation. So some of the forces in the x direction must be equal to 0 because our acceleration in the x direction is 0. And we don't have any forces in the acceleration, so we're good to go here. Some of the forces in the y direction must be equal to the mass times the acceleration in the y. We have this value. We have mass as well. So we have those values known. So that's going to be equal to forces in the y. What are those forces going to be? Just basically F1 plus F2, right? Again, we're ignoring essentially our gravity component in this problem. That's one of the other idealizations, but this is one equation. Then finally, some of the forces, so our body is basically rotating through here. So we can say sum of the moments about G equals IG. So actually we can solve it like this, and we can also solve it another way as well. Sum of the moments at IG is times alpha, because we already have our angular acceleration, and that's going to equal, and we can kind of draw so if we're taking the moment about here, we have two forces. So if I'm looking at the line of action here and here, those are going to be the same perpendicular distance here. So this is going to be plus F2 times 0.25, and then it'll be minus F1 times 0.25, and we got it. So let's go ahead. Let's define some values here first, and let's get going in Mathematica to solve this problem. So we're going to have our mass equals 0.05. We're going to get our, we don't need the diameter here, so AY is equal to 10 meter per second squared. Our angular acceleration is going to be alpha. That's going to be equal to 20. Our IG equals M times our radius, which is going to be 0.25 squared. 0.25 squared time, and then this whole thing divided by 2. Let's go through here. We're just typing it through just to make sure that we're good to go here. Divided by 2. And then, so let's define these. Now let's get into our equations below here. We have two equations. We have two unknowns, so we can solve for those. So let's just set them up. So let's set up over here. So our equation Fy equals mass times AY set that equal to F1 plus F2. And then our mg is equal to I, sum of the moments about g, ig times alpha. Set that equal to F2 times 0.25 minus F1 times 0.25. You can get that. Now we're going to solve Fy mg. And there we go. So we have our values. Fantastic. We could also have solved it, again, another way using our definition of basically the sum of moments around a point as well. So how could we have done that one? Well, let's go ahead and let's break it down. So let's say I didn't do this. Let's say we did sum of the moments. So let's instead use our other definition. So we're going to say that the sum of the moments around point 1 that we have here is going to be equal to the sum of our kinetic moments. Let me put that right there. Kinetic moments about point 1. So that's, again, let's go back here. That is really this definition that we, way back. This is what we've defined previously. So this is our kinetic moments about point P. So some of the moments from the forces, some of the moments from the kinetic actions of our body. So let's go ahead and let's break that down, because this is a good example on how to do this. So some of the moments about point 1, what would that be? So just from the forces, it would just have to be force 2. So that is positive in our notation. So force 2 times 0.5. That's the only moment from our forces. Now, we do have some kinetic moments. One will be mass times acceleration in y is going right here. The distance between these two, it'll be 0.25. And we also have this IGA plus IG and then alpha. So that's kind of the critical aspect here. Those are going to be basically our kinetic moments that basically emerge from this system. So you sum those about that point, and now we're going to be able to go ahead and solve our problem now. So let's go ahead and let's do it. So let me clear this. Actually, excuse me. So let's go ahead. We had mg, so let's have m1 now. m1 equals F2 times 0.5. Set that equal to mass times AY times 0.25 plus IG times alpha. And then now let's solve Fy m1. And isn't it great when it all comes together? Fantastic. So we will see you in lots of other practice problems, but now we're going to get into vibrations, which is a cool concept, and you're going to do a really fun lab on this. So we'll see you in the next video. Thanks. Bye.